All right. I hope everybody had a good lunch break. I would like to go ahead and get us started back into the technical part of content. So we're basically just going to pick up kind of conceptually right where we left off. So this is, I originally called this advanced Fourier analysis. We'll touch upon like maybe legitimately advanced Fourier analysis, but this is really going to be much more about non-trivial applications. So in the first lecture, our kind of big goal was to characterize time series. Now we want to be able to sort of model processes that act on time series. And to do that, we'll invent convolution. And from convolution, we'll study two applications. One is filtering, and the other one is sampling. And then we'll derive a theorem called the sampling theorem that I never really got a presentation of. I think at any point kind of in my formal education. A lot of people have one result they know about sampling and they use it all over the place, even when it's inappropriate to use. And so I'll present the exact statement of the sampling theorem. That will be kind of a nice application of these techniques to solve a real problem that you will encounter in research. Okay, so so here are the goals. So I think I said, so far we've seen just a single signal that we tried to characterize. What we want to generalize that to is multiple interacting signals, where the interaction between the signals does something to the process that we're interested in learning about. And so we should ideally be able to generalize to that multi-signal space. So as I mentioned, this is going to be called convolution, and convolution allows us to perform convolution-like operations in either the time or the frequency domain. And so we'll see what that looks like in both domains. And then we'll introduce filtering and then discuss observations that are discretely sampled using this kind of framework. The last thing, as I said, will be some actually legitimately advanced concepts. So the first will be wavelets, which we'll learn more about in the match filtering lectures on Thursday. And then I also wanted to mention something that I'm starting to learn about, which is Fourier analysis on finite groups, which is how you understand or apply these concepts towards convolutional neural networks, right? A more generalized framework for understanding the math of modern machine learning. So as I mentioned, these are all the same resources I gave earlier. Seriously, if you have any questions or find my presentation unclear, Osgood is a really, really nice set of lecture notes. And then these two references go into some aspects. Most important part of my lecture. Okay. All right, so I'm going to start with presenting the convolution theorem. So as we talked about this morning, there are functions of time, f of t, that we can call signals, and we can characterize that through this operation called the power spectrum, the power spectral density, p of k. And these things are roughly related. It's not quite f of t and p of k being related by the Fourier transform. It's the correlation function, not the function itself, which is just, we talk more about that subtlety, but basically these are kind of equivalent ways that astronomers use to describe signals. So the Fourier transform takes functions defined in the time domain, turns them into functions in the frequency domain. And as I mentioned, the Fourier transform is an operation on functions. It's not an operation that intrinsically lives in either domain. It's an operation on the function space themselves, and it changes the functions from living on one domain to the other one. Things are not perfectly rendering the way I'd like. That's okay. So the Fourier transform is additive. So as we saw, if I take the Fourier transform of the sum of functions, I get the sum of the Fourier transforms. So another way of putting this is if I add the signals f of t and g of t in the time domain, that will sum the amounts of Fourier transform of g and the Fourier transform of f. I'm using s in this lecture instead of k, but it's frequency. So basically, you sum the Fourier transforms. So if I add two signals in the time domain, I just add their Fourier transforms in the frequency domain. And we can do something similar for products. So if I have a multiplicative constant, I can just pull that out and multiply through times the Fourier transform. One note on notation. So when I take a Fourier transform, this argument here is the argument in the domain that the Fourier transform has taken my time domain function to. That's a little confusing. So because I've taken the Fourier transform of this function f, the argument is in the frequency domain, not the time domain. So that's a notational thing that I often got confused about. I get questions about that. So if I wanted, yeah.
Sorry, does it matter if the alpha is real or complex? Doesn't matter, I assume.
I don't think it matters, but that's a good strategy to think about. Right? So this may only be, yeah. I don't think it matters. I think you can just pull out the complex. That's a good question. So what if we only wanted to change some frequencies but not others? So in these expressions, I've been acting on all frequencies simultaneously. What if I only wanted to act on some frequencies? So the operation that will allow us to act on some frequencies but not on others is going to be called convolution. And as I mentioned, this is going to let us filter signals, sample, and ultimately from sampling, I'm going to be able to prove a theorem about what it means to interpolate a signal as well. How well can I create a model of a signal given some discrete sampling of that signal? So that's the connection between sampling, filtering, and interpolation. So what we want is a function that takes signals in the time domain and produces a combination which corresponds to their product in the Fourier domain. So in other words, what operation do I act on f of t and g of t such that the Fourier transform is equal to the product of g of s and f of s, the product of the Fourier transforms. So it turns out that this is, okay, I think I'm gonna, let me try re-rendering this guy. There we go. Okay. So this question, I think, this question of what operation acting on f of t and g of t corresponds to products in the frequency domain sounds like a hard question to answer. It turns out that you can actually derive this pretty simply. All you do is you write down the Fourier transforms of your two signals, f of t and g of t, take the product, and if you make this clever change of variables, just to use substitution, you will end up with this expression for something called h of t, which defines a convolution operation. So I take the integral of my g function shifted for different values of x times my f function, and I integrate over all values of x. And that function, it turns out, is the thing that if I take the Fourier transform of it, so originally I take the Fourier transform of h of t, so that gives me something in the Fourier domain, which is why this argument is s here. So the Fourier transform of this thing is equal to the product of the Fourier transforms. So convolution is the operation in the time domain that corresponds to multiplication in the frequency domain. Yeah, so this result here is called the convolution theorem. So what is convolution? So there's a very famous visualization of this. It's actually kind of funny. You used to be able to Google for the visualization where you have two functions sliding past each other. So doing that g of t minus x for different values of x, and you would get a nice picture of what the convolution integral is. When I Googled to try and find that animation, all I found were animations about convolutional neural networks. So my office mate correctly suggested that it might have something to do with my personalized search history. So I went into a private browser and I got the same result. So I was not able to find a classic animation, but you all have probably seen it. If not, you should go look it up. But this is a static version of it. So I have two functions. If I move this function past this function, keep that integral, I get like a triangle thing where it peaks in the middle and sort of dies off on the sides. So at a given value of, it's got to be, this is a typo. This is the convolution of two functions. What it is it's a weighted average of one function near a certain value of t. And then as we allow things to vary, we're sort of smoothing two functions together. So a nice kind of result or a nice intuition is that the convolution of two functions g and f is at least as smooth as each of the two functions are independently. So convolution is a smoothing operation. You take, and you can kind of actually see that in this here, right? You have these two functions which are definitively not smooth, maybe the least smooth functions you can imagine. You take a convolution of them and the triangle is somehow smoother. Though I kind of wonder about that as a technical statement, given what we talked about discontinuities and derivatives, right? Whether the derivative is continuous. So yeah, so one thing to be careful about is that convolution, as we defined it here, is an operation over all values of f of x and g of x, and it yields values of the convolution function. So it's a smearing and smoothing operation. So some useful convolution properties. So as I mentioned, one thing we can do is we can then filter. So filtering is an operation that modifies the spectral content of an input signal. One reason you might try and filter a signal is if you only care about some frequencies but not others, or it could arise as a way to understand the behavior of some dynamical system. So I talked about this paper that I wrote a few years ago, but it turns out that spin-orbit couplings, because of a damping term that appears in the rotational response of a icy satellite, like one of Jupiter's moons, you would actually end up with a very distinctly, very sharply peaked filter that can really amplify and potentially basically measure a term that depends on the ice shell thickness for Jupiter's moons. So if you have frequencies that are near a frequency corresponding to the thickness of the ice shell, the rotational response will be really enhanced. So it's not just an analysis thing to try and filter your signal, it's also a thing that appears in the actual behavior of real physical systems. Okay, so as we just saw, so the operation that corresponds to frequency domain multiplication is convolution in the time domain. So we can understand filtering as an application of convolution. So in the frequency domain, I have some new signal, W of S, and that's going to be equal to some filter function that I'll define times some function in the frequency domain that I'm interested in. So some input signal, right? The Fourier transform of some input time series times some filter gives me some filtered function. So as I just said, the appropriate procedure to do filtering is to take a time domain signal, in this case v of t, perform the Fourier transform to obtain its Fourier transform d of s, then multiply it by the frequency in the frequency domain with some filter that I've defined in the frequency domain, and then Fourier transform back, and I'll get a filtered version of my time series with only some frequencies present, or some frequencies that have been changed. So some properties of filtering. So filtering can't add frequencies to the spectrum that weren't present in the input time series. So filtering can only, it's basically because when you multiply by 0, you still get 0, right? It's a multiplicative operation. So I can change the amplitudes and the relative contributions of any frequencies that existed in my input time series, but I can't create new ones, right? However, if I have a filter that is 0 somewhere, because I can multiply by 0, I can remove frequencies from the recovered time series. As I said, it can change the amplitude, it can't add new ones, and real value filters don't change the phase of the input signal, but if I have a complex value filter, that can change the phase of the recovered signal. So something I always thought was confusing is that a high pass filter removes low frequencies, and a low pass filter removes high frequencies. Right? It's passing the low frequencies, or it's passing the high frequencies. Okay, so that's one application, filtering. The other application is sampling, and also these operations called, or these functions called Dirac deltas, right? And you've probably heard that a Dirac delta function is not a function; it's a distribution. And so we're gonna define what a Dirac delta is. Yeah. Sorry, there was a couple of questions.
About the filtering.
Yeah.
Since it's all done in frequency spaces, how do you develop an intuition for what is a good filter since you want to answer back out in time in space?
Yeah. So you can define. You can say what you do is you say I want a filter that. Well, we'll talk more about this, right? But oftentimes what we'll do is we'll define a filter in the time domain, take its Fourier transform to get its form in the frequency domain, multiply together, and then inverse from it, right? So it's usually intuitively easier to work in the time domain. The reason I'm hesitating about that is that often what you want to do is you want to remove certain frequencies, in which case it is easier to write down a filter that is just like a step function where all frequencies in the frequency domain are kept, and that's what I had to do with the problem set. Let's write that down.
Right.
Yeah, sorry, there was one more. Yeah.
The thing is, like, if you have a time reference from then you have to start changing it to the frequency, like Fourier transform.
Yeah.
You multiply by another like frequency domain.
Yeah, so here we take the signal in the time domain, which is lowercase v of t, and here I'm using uppercase v of s to describe its Fourier counterpart. So you take the Fourier transform v of t, you get v of s, and then you multiply by some filter that you've defined in the frequency domain, or the Fourier domain. And their product is the filtered signal in the frequency domain. If I then Fourier transform this thing, inverse Fourier transform this thing back into the time domain, now I have a filtered version of v of t that will only have some frequencies present, or it'll have the frequencies, their amplitudes will have changed, right? But it won't have any new frequencies.
So the interface depends on the problem. How you do it.
Yeah. So this is what you're interested in, right? So in the example that I gave of icy moons with decoupled ice shells, like we derive this thing from physics arguments, right? So there's a physical form of the filter, and then we multiply by the rotation state of the satellite. So it's a vector that encodes the rotation state. So. Okay. Are there other questions about filtering? Okay. So ultimately, what we're gonna actually like sort of, we're not gonna quite derive it, but I'm gonna give you the statement of the sampling theorem. So we're gonna get there by showing that a signal can be reconstructed from a discrete set of samples of a function. And so we're gonna need some function called the Dirac delta. It'll actually be sums of Dirac deltas that will allow us to sample functions, right? And the big idea here is that we, as scientists, we never have access to a continuous function in the time domain. We always have a set of discrete points that we think represents some model that is continuous. So we want to know how well we can reconstruct that continuous model from a set of discrete real observations. And so what we want to do is we want to come up with an operation that takes a continuous function and says, I'm sampling at these points, and we want to know how that function affects our ability to reconstruct the model. So as I alluded to earlier, so function is in quotes because the Dirac delta is not actually a function, it's a distribution. But we're gonna use them to define sampling, construct the interpolation theorem, and we'll show explicitly why the Nyquist frequency gives an appropriate limit for sampling. And I want to stress this because the Nyquist frequency is a piece of jargon that a lot of, especially astronomers, know, but a lot of people haven't sort of worked through where it comes from, and so sometimes they misapply it. So, as I mentioned earlier, so we start by looking for a broader criteria for when a function has a well-defined Fourier transform. So, the issue with this L1 integrability condition, as I think I may have mentioned this morning, is that there are functions that have well-defined Fourier transforms, but don't have inverse transforms according to this definition. So their Fourier transform is not L1 integrable. And so it doesn't, so sorry, if I take a function, take its Fourier transform. If its Fourier transform is not L1 integrable, according to this criteria, then that function would be said not to have a well-posed Fourier transform since it doesn't have an inverse operation. And one of our conditions on the Fourier transform is that we can go back and forth. It turns out that we can generalize to capture all of the L1 functions, as well as all of these functions that don't have a well-posed inverse, by looking at, let me see if I think I have this as my next slide here. Yeah, so by generalizing to a class of smooth and rapidly decreasing functions. So if a function is smooth and rapidly decreasing, it's not necessarily an L1, but it has a well-defined Fourier transform and it has a well-defined inverse. And so we've replaced our L1 criteria with this L1 criteria. And the bit of jargon in the math literature is these are called Schwartz functions. So yeah, so a Gaussian is an example of a Schwartz function. Yeah, question.
Yeah, when you say that the criteria that we were talking about before and how it's important to go back and forth, is that a mathematical reason or just like a convenience?
I mean, a little bit of both, right? So, I mean, in math, you can define whatever, like, you define the operations that you care about based on what you want them to be able to do, right? So we could stick with that earlier L1 condition, and we would just lose out on a lot of systems having Fourier transforms that appear in physics, right? So like, if you go through Osgood's notes, he gives you a ton of examples of functions that would not, according to the L1 criteria, have Fourier transforms that you want to have Fourier transforms. So just a aside, because this, yeah.
Yeah, and just to add to what you just last said, can you maybe mention any prominent functions that we, Fourier functions that we use in astronomy? Like
it could be misremembered, but I think the Gaussian
yes,
is an example, right? So you want a Gaussian to have a Fourier transform. So that's what this sentence is saying. Okay. Yeah.
Is there like a descriptional difference between a function and a distribution in this context? Is a Gaussian function different than a Gaussian distribution?
What was that?
Is a Gaussian function different than a Gaussian distribution? Is a Schwartz function different than a Schwartz distribution?
So
Or again, it's like
Let's-
parentheses there.
let's put a pin in that question, and I'm going to talk about what a distribution is, and then we can come back to that. Yeah. So the idea behind a distribution is that a distribution is a thing that acts on the Schwartz function and returns a number. So a Dirac delta distribution is going to act on a function, and it's going to return the value of that function at a point. So this is the thing that we want to be able to do to sample things. So what we've done is we sort of generalized, right? A distribution is a kind of operation, and it's an operation that acts on function spaces. So, so this is a bit more jargon, but this is the notation. So if I have a distribution T of f that is corresponds to some function f of x, then the action of that distribution is given by this integral. So yeah, so this is how you get to, the reason I included this, I should have been a little clearer. The reason I included this is you've probably seen this kind of statement that if you integrate over a Dirac function, or a Dirac delta function, that you get either 1 or 0, but somehow there's like infinite area. This is a better way of sort of writing that. That these distributions are defined by these integrals, and it's defined by the kind of thing that you get back. So a delta function is the kind of thing that returns the value of the function at a point. So either at 0 or suitably shifted. I'll also mention there are other ways of defining distributions. I like this way of defining it because it's saying that I have these things, in this case Dirac distributions, they act on functions in a certain way to do sampling. So this is some results about distributions. So the value everywhere. So the value of the Dirac function is somehow 0 everywhere except at 0, and at 0 it's infinity. But if I take the integral over the Dirac function, I get 1. So this is sort of what I was saying earlier, is that we can either look at things in terms of this notation, where I have the distribution on the function, and it gives me a thing, the value of the function, or I can define it explicitly in terms of these sorts of integrals. Let me see, are there anything else that's really? I don't think there was anything else I really wanted to mention.
So in the last example, like DA, that means can I compare DA with the delta? Like that is also the direct distribution. T of it you mentioned in the example that was that means T of it of x is equal to 0 and T of it of 0 is equal to infinity.
Yeah, you can just sort of plug in the delta function, right? The delta function is the distribution. It corresponds to this function. Let's see. So, so an important result is that the Fourier transform of a delta function is equal to 1. And this is just the proof of that. So this is just manipulating the definitions that I gave on the previous slide. And you can also show that the Fourier transform of 1 gives you a delta function. So we can go back and forth from the Fourier domain to the time domain with delta functions. You can also show that for a shifted delta function, so something shifted away from the origin, that the Fourier transform is this complex exponential. Yeah.
1 is the function which is 1 everywhere.
This is the number 1. Yeah, this is 1. Yeah. Yeah, it's not a one. Yeah, sorry, to answer your question, right? Why is that? Because this delta function is a little zero. This is the delta function at the point, right? Here, this is a delta function that's shifted, and the Fourier transform of the shifted delta function gives you a complex exponential. The Fourier transform of this back gives you a delta function. So, sorry, is there a question? Why is this? Yeah, because there's a unstated, let me go back this for a second. I think this is using this result here, and so there's a 1 here, which allows you to pull this 1 back out to the notation. I think that's why. I can double check. Yeah, I remember having that question when I put this together. I thought I clarified it for myself, but I guess not. So, notes for next time we get this slide. Okay. So, it's a lot of formalism. I really just wanted you to have seen that formalism. So one application of the delta function is to write down a way to sample, first to write infinitely periodic functions. So we'll call a function that acts on another function make it periodic. This symbol that I can never pronounce, C, can't write it either. So this is called, well, let me come back to that. So we can define it as a sum of delta functions. So we can see that if we apply this operation to functions, we get these sums that are telling us what the value of the function is at different points, right? So if I convolve a function with this sampling operator, I get the sum of the value of the function. So involving f of x with c gives us, sorry, this is actually, I'm skipping ahead a second. This is giving us a periodically shifted version of the function, rather. It's not sampling the function, it's giving us a periodically shifted version. So convolution of this C operator with f of x gives us the periodization of f of x. So, so we can also multiply by PC, and this is the thing that's gonna let us, is that this is the thing that does sampling. So convolution periodizes the signal, multiplication does sampling. And there's a result, a fun result, that the Fourier transform of C is C itself. So this allows us to ask and answer a question, which is given a signal f of t and a collection of samples of the signal at different times, can we express the values of f of t as a function that's evaluated at those sample points? So the answer is yes, of course. So this is where the sampling theorem comes from. So to prove it, and I invite you to do this, is apply C to the Fourier transform of f of t, then cut off the Fourier transform to a finite range called P. So this is called making a signal band limited. So if a signal is band limited, it's confined to a certain range in frequency space. And this will, so this allows you to describe a signal with some finite sample number of frequencies. And then if you do that and take the inverse Fourier transform back, you will get the following result. So this is the sampling theorem. This is the actual statement of the sampling theorem, not the factoid that people often repeat, which is the Nyquist frequency. So f of t is equal to a sum of these kinds of functions, and this function is evaluated at values k, frequency points basically, divided by the bandwidth of the signal.
So is that a regular sine function, or is that a?
This is a sinc function. So this is actually that function that I showed, that we saw earlier, that is the Fourier transform of direct function.
Oh.
Yeah.
What's the sum of it?
The sum is over the frequencies. So an infinite set of frequencies to describe it. And actually, in this case, this is a continuous signal, so we need an infinite set of frequencies. So in practice, you have a finite number. Yeah.
So like in general, like we do for filtering response like for like sampling, like what's the target to reduce the noise or?
So sampling is all real signals are sampled. So we need methods that account for the fact that all real signals are sampled. And so what this is doing is this is putting a limit on our ability to reconstruct f of t based on how often we've sampled. So more data always helps us better construct whatever our actual time series is what this is a statement of. Right? In practice, we only have finite frequencies, and so you can only reconstruct a signal with finite resolution. And because of that, there's an effect called aliasing, which I give you a problem to work through. Yeah.
Going back to what you said, the Fourier changer, resides itself, but how profound is that statement? Is that a very rare thing? If there's some implication of that in the case that makes psi act the way it does, or is it just like a coincidence?
I think it's a profound statement, and not being an electrical engineer, I think I can't tell you why it's a profound statement, but I think it's a profound statement. Yeah. So the takeaway is there some limit on the number of discrete sample points that we need to describe a signal? And this is called the Nyquist frequency. And the intuition here. Yeah. This point probably should have been on its own slide, but the interpolation formula depends on the bandwidth. So that means that this only applies to band-limited signals. So a point that Adam emphasized in his lectures is that non-band limited signals, this doesn't apply to. Things that are not strictly periodic, there's also problems with. So you should be careful when you cite the Nyquist frequency, because people often cite the Nyquist frequency without having checked the conditions under which this argument is true. But the result is that if the spectrum runs from a frequency, sorry to change notation again, but mu min to mu max, we need to sample with a rate that is at least twice the highest frequency. So why is that? If I'm describing a signal by some approximation of with an amplitude, a frequency, and a phase, I'm going to have at least three. I need to have at least three equations to get straight each of these three unknowns, which means I need to sample at least twice every frequency that's present. That's where it comes from. But to formally derive this result, there are some other conditions that you should always check before you cite the Nyquist frequency. Yeah.
Could you not like rotate your system such that your phase goes away, so then you only have two unknowns?
Yeah, that's why there's an equal sign. Right? So you need to do it at least 2 times, right?
No,
So, yeah.
sorry. I'm saying for the omega t plus phi.
Yeah. So yeah, you could do something like try and get rid of the phase by redefining the time variable, right? That's why it's at least 2, right?
Oh, okay.
3 is a good number because that allows you to constrain the phase behavior as well. But you need to get at least 2. You can't get away with measuring. You can't tell what signal you're actually looking at if you only have one sample corresponding to that frequency. So any frequencies that you don't sample, at least the Nyquist rate will be unresolved. And so this is going to be translated into the frequencies that you do, right? So by Parseval's theorem, the total energy in the signal is conserved, right? So you're going to see that frequency show up in some other frequency. And this is something called aliasing. And I think I worked out a nice simple problem for you to see how aliasing works in the problem set. Okay. So that might have already been a lot. I feel like the morning was a lot. I see a lot of shocked faces. So I'm gonna say even more complicated things. I'm writing my choices now, but press on. So I'm gonna talk about wavelet transforms and generalizations of Fourier analysis to finite groups. Okay. So wavelets. So the Fourier transform is an operation that takes signals that are localized in frequency and converts them into continuous signals in the time domain, or vice versa, continuous signals in the time domain and turns them into localized signals. Goes back and forth, right? So in the time domain, things are continuous, in the frequency domain, they're discrete, or vice versa, right? That's the Fourier transform. Can we construct an analogy to the Fourier transform that takes signals in the frequency or the time domain to signals that are localized in its Fourier transform space that are localized in both time and frequency? So rather than having this trade-off between localization in time or frequency, can we construct an operation that is localized in both time and frequency and somehow optimize trade-offs? Obviously, I wouldn't be asking questions. The answer was no. So the thing that can do this is called a wavelet transformation. And I'm familiar with these in cosmology. They're increasingly popular for like weak lensing analyses. But I'd be really curious to hear if anybody knows of any applications in other branches of astronomy. As an open question, if anybody knows, would like to chat. Yeah. Yeah.
I played with this a little bit for looking at differential rotation in stars.
Yeah. Is there a specific advantage to the wavelet transformation for likelihood analysis?
Yeah, it can help kind of disambiguate some of you have a period that shows up in the light curve that changes depending on where a spot is on the star because of differential rotation. The period is actually different, and so that gets kind of varied in most other forms of cryogram.
Okay, awesome. Yeah. So yeah, I wasn't going to say a great deal, but just introduce. The idea is to construct a bank of wavelets. So I have a whole family. So rather than just like projecting on the complex exponentials, one k value after another, I have a whole family of these, and they've got two parameters, j and theta. So this is a rotation matrix, and this is some sort of like analogous to a Fourier frequency. And so I'm going to rotate these things, and they'll have a amplitude and an orientation. And I'll measure the amount of the signal that corresponds to each scale and orientation for each element in my family of wavelets. So I take the convolution of my input signal with the wavelets, and this gives me my wavelet transform. Unfortunately, I was going to give you all a problem to play with wavelets. There's a really nice package, and that's one at a conference who developed it pretty recently. It makes this thing really, you can see all sorts of really cool applications from them. Makes it really easy. It doesn't run on new model MacBooks, which I think most, at least a good fraction of us have, so I didn't give you a problem. But if you're interested in doing this, I'm happy to walk you through how to do a wavelet analysis and have a full work example. And we'll also see a little bit more because this is closely related to the notion of matched filtering, which we'll have a whole lecture on and some problems. Okay. So wavelets are one way of sort of generalizing Fourier analysis to get you some information about orientation and sort of define a family of basis functions. But I want to give you another insight into thinking of convolution and Fourier transforms as encoding symmetries in problems. So this is going to be a little bit abstract, but it's really just to give you an idea how this might work. The idea is that convolution has something to do with shifts in one function, g of t. So it's somehow saying if I shift a function over, it's the same function, that there's some shift symmetry in the problem. So we can suppose that there are some matrices that define the space of shifts in the vector x, left or right. And these are we're going to call these discrete shift operator matrices. So it turns out that the Fourier basis are the eigenvectors of these discrete shift operators. And so I can then define sort of a diagonalized version of this, which will allow me to write down convolution. And so for every matrix that corresponds to a symmetry, I can find its eigenvalues and come up with a kind of Fourier analysis for that symmetry if I can come up with a representation in a matrix of that symmetry. So if I have a bunch of shift operator matrices, I get convolution and the Fourier transform as sort of the cross transformations that preserve that symmetry. I think that's all I wanted to say about this. Yeah.
What do you mean by symmetry in this context?
So in this case, it's if I shift the signal left or right, or I wrap the signal back around itself, it should be the same signal. So the Fourier transform, since Fourier transform tells you what's happening on cycles, and it's because it's encoding this shift symmetry. If I cycle back around, I get the same function back. And so the eigenbasis for matrices that do that gives me convolution, gives me shift operations, gives me the Fourier transform. Okay. So this is the modern perspective on how things like convolutional neural nets can be tailored to respect symmetries in your problems. As I said, it's kind of shifting things back around, so it all comes full circle. And that's all I had to say. So. I think, I actually deleted this problem. So it's just these three problems. So a low pass filtering problem, a discussion of optimal filtering, and then some intuition for how sampling and aliasing works. Or you can do problem 4 from the morning problem set. And I will post these problems to the GitHub right now. So feel free to take a 2-minute break or something.